We're going to continue our discussion of functions, and we're going to use a really useful tool for functions, graphs. And these are really visual representations of the relationships between the independent and dependent variables of a function. And so I wanted us to remember that with this visual image of glasses, that graphs are really a tool to help us see these relationships more clearly, and they're very powerful. And the first example I want to look at is this graph here that I got out of the New York Times. It's a graph of the 7-day average of new cases of COVID from March through mid-August, and over here are the number of those new cases. And this is for the state of Arizona. We're going to call this function that's represented by this graph n of d. And the n part of the function represents the number of new COVID cases, and we look at the 7-day average. That's a really useful metric. It sort of smooths out the data, so if you have a kind of a day that's an anomaly, it doesn't throw everything off. So the 7-day average is a metric that's often used. And the d is going to represent what day it is. With function notation, whatever's inside the parentheses is our input, or what we've been calling the independent variable. And this is days. And n will be our output, or our dependent variable. So n is our dependent variable, and d is our independent variable. Looking at this graph, we have a sort of vertical axis and a horizontal axis, and we'll have that with any of our graphs. The horizontal axis always represents the independent variable, and we can see that in this case. The horizontal axis is representing days, so d. And here it is, our independent variable inside the parentheses. And the vertical axis will always represent the dependent variable, your output, which in this case is n, the number of COVID cases. So we have the dependent variable going along the vertical axis and the independent variable going along the horizontal axis. And we'll ask some questions and answer the questions. The first question that we're asked is to estimate n of August 1st. Okay, so this is our input, August 1st, and they're asking us for n, the number of COVID cases. So I'm going to go to my graph along the horizontal axis, and I get to August 1st right here. And I go up to see where the red line, this guy right here, is our graph of the function. So from August 1, I go up to see what value the function is. And it looks like it's right here. So then I see if I can estimate that number, and I would guess it's probably around like, maybe like 2,500. So we say that n of August 1st is 2,500. That's our estimate. And that means that on August 1st, the 7-day average of new cases was 2,500. The next thing that we need to do is estimate n of July 1st. And I actually changed the equal sign to these little squiggly lines that just indicate that we're estimating. Okay, July 1st, we go along our horizontal axis. Here's July 1st right here. And July 1st, we want to know what is the function doing on July 1st. So we go up to see if we can estimate a value for this. So let's see, about right there. And then I have to find what that value is on the dependent variable axis. So I'm going to say that's like 3,300, 3,400 maybe. Okay, so the number, 7-day average of new COVID cases, July 1st, we say is 3,400. The last question is going to be a little bit different. This question asks us to solve for d in this statement, n of d equals 1,000. So we have to think of, in this context, what is this talking about? So some n, some number, is equal to 1,000. Some number of new COVID cases is equal to 1,000. And we're solving for this d right here. What is the day where the new cases are 1,000? Well, a good way to do that is to go to 1,000 on our dependent variable axis. We know that this is 1,000. Now we're going to kind of go across like this and find what day does that happen on. So this time we knew the opposite variable. We knew the output variable, and we're looking for the input variable. So we know the output variable is 1,000. Bam. So right about here, oops, maybe about, I don't know, June 10th. But then we have to ask ourselves, does it ever happen again? And it does. It happens a little bit later, right here. So maybe like August 7th-ish. So 2 times we get the number of new COVID cases being 1,000. And so we have to account for both of those. So knowing that there were 2 input values that gave us an output of 1,000, we indicate that here, that d equals June 10th and d equals August 7th make this statement true. Okay, hopefully this example gives us some practice in using our function notation. We want to become really familiar with this, knowing that this is our input variable always, and this is our output variable always, and being able to read off a graph different aspects of a function that we're asked. For this next example, we're given a function, and it's described in this form with a formula. This is really the most common way we're going to see functions, and so we want to get some practice with this. So here we have our input variable x, and then this is the rule. This is sort of the assigner. The function tells us to take your input, and you're going to take the cube of that input, and that's our new output. And we are going to draw a graph of this function to get an idea of what it looks like graphically. But before we do that, we're going to create a table of values here where we'll put in some inputs and we'll evaluate the outputs. The first column of the table will be x, and the second column will be f of x. And f of x will often be called y because we're going to be using an xy coordinate plane, and the y represents our outputs. So I sort of choose some input values, and with these input values I'm going to figure out what my outputs are. So -2, if this is my input, the function says to take that number and cube it, and the answer will be in this part of the table right here. So -2 cubed is -8. Same thing for -1. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1, and 2 cubed is +8. So this is great. This gives me some values for my function, and I'm going to put them on an xy plane and graph it. So here are my axes. I've got a horizontal axis x, which will be my independent variable, and I've got a vertical axis f of x, or y, which will represent my dependent variable. I put some hash marks on just so I know where I'm going, and I start with my first ordered pair. If x equals -2, then y or f of x equals -8. So I'll go -2 on my x-axis and -8 on my y-axis, and I should get a point right about here on my graph. Same story, -1, -1, so -1, -1, and I'll get another point right here. 0, 0, x equals 0, y equals 0, gives me a point right here. 1, 1, x equals 1, y equals 1, gives me a point right here. And the last one that I've got on my table, 2, 8, 2 in the x value and 8 in the y value will give me a point right there. And I could get as many points as I wanted to, but this right here gives me a good idea of what the function looks like. So I'll just sort of sketch it out. It's kind of, oops, got to catch that point. And then flip up and get this one. And the function does keep on going infinitely, so I'll draw some arrows to indicate that. So we've got one function represented with a formula, with a table, with a table here, and with a graph. And so we have a pretty good picture of this function. These are all representing the same function. It's just like different pairs of glasses. We can see different things with the different representations. The first question that we're asked is to solve for x, this statement, f of x equals 27. We saw one like this in example 1. So what we want to remember, this sometimes a question like this can trip students up, but what we want to remember is the fundamentals of function notation. What does everything represent? So this is our input value. So this is the part we don't know. This is our output value here, the 27. And so this is the part we do know. What is our x when our output is 27? So gosh, it's not even on this graph, it's not even on this table. So we have to kind of think back through this function. When the function output is 27, what was its input? What number here would lead to the 27? So in other words, what number cubed equals 27? Well, we know that. We know that x equals 3 would be a solution, that x equals 3 cubed is 27, and then we think, are there any other numbers that could lead to 27? How about negative 3? No, that'd be negative 27. So this is it. This is the solution. We found the x that they asked us to find. Okay, for this problem, we're asked to evaluate f of negative 4. And again, we just want to think of function notation. What is everything representing? So we have this function f, and it's this guy right here. And they're asking us, when the input value is negative 4, what is f of negative 4? What's the whole function? So when our input is negative 4, essentially they're asking, what is the output? What is the function evaluated at negative 4? We don't have any inputs of negative 4 here or here. Let's go back to our formula for the function. So if our input is negative 4, then that would mean that we want negative 4 cubed. That's the rule for this function, and negative 4 cubed is negative 64. That's it. That's the answer that they're looking for. Now for example 3, a very important topic, duck population analysis. Okay, the duck population in Earl Jones Park has been estimated to have a birth pattern described by this function. A birth pattern described by this function. Here, t is time in years, with t equals 0 corresponding to 1988. Okay, so that's important. N of t is the number of births that occurred during the year t. So, if t equals 0, that's 1988. So I could expect in 1988, my input would be 0, this would be 0, this would be 0, this would be 0. In 1998, I could expect the number of births to be just this number, 750, for example. Okay, this is a great problem. We're going to go to a graphing tool called Desmos. You can get this on your phone. It's a free app. You can use it on your computer at the website www.desmos. I think it's com, maybe org, but just search for Desmos. And we're going to get a picture of what this function even looks like. And Desmos is a great tool to use. I recommend everybody get that app or use the website. Okay, so I'm going to input that function for duck population into Desmos, and they prefer Desmos doesn't really like the variables n and t as much as it likes x and y, x as an input and y as an output. So we could either call this y equals 3x cubed minus 36x squared plus 108x plus 750. So that would input the function. You could also call this f of x. Both names would be fine with Desmos. And when I input that, I can already see that my function, I'm not getting a really good window on my function, and that's because I'm going from negative 10 to 10 on my inputs and from like negative 10 to 10 on my outputs. Well, I already know that the duck population is going to be a lot larger than that. So I'm going to go up here to my tools icon and change kind of my range. My x-axis, I don't really care about negative time, so I'm just going to go from -1 to maybe 15 years out. And then y-axis is modeling the duck population. So, and that should be a positive number. We'll go -10 just to, be able to see where the axis, the horizontal axis is. But we should go up to, I'm going to try like 1,000 and see what that looks like. Okay, that looks a little bit better. So this is a model for our duck population. And when that time is 0, I can see that my population is going to be about 750.
well, we'll talk about all of this, but this is how I input the function into Desmos, and I did have to adjust the values of my x-axis and y-axis, and you'll often have to do that. So I've gone ahead and graphed this function, and it looks like this. I'm glad that I didn't have to do it by hand. That would have been kind of a pain, but Desmos is awesome. It helps us get a visual representation of what's going on with this function. So think for a minute, what will the horizontal axis represent? The horizontal axis is always the input variable, and in this function it's representing time, time in years, and it's years since 1988. Okay, so we know that that's what this horizontal axis is representing. So 10 years right here, if we were at 10 on the horizontal axis, we would know that that's representing 1998 because that's 10 years after 1988. What's the vertical axis representing then? That's our variable n, and it's the number of births that occurred during that year. So number of duck births. So number of duck births in a particular year. Now that we know kind of what all this stuff is representing, we can answer a series of questions about the years and maybe the duck births during a year. And the first thing we're asked to do is to estimate from the graph the number of births each year from 1990 to 1993. Okay, 1990 is 2 years after 1988. So 1, 2. In 1990, I go up to the graph, and this looks really close to 900. It's slightly below 900, so maybe we'd say like, 890 or 895 would be a good estimate. So I hope each of you caught my mistake. When I said this was slightly below 900, there's no way that's true. This is not 900. I mean, if this is 800 and this is 1,000, 900 is like right here, right? So this is 850. So this is about 850. And so for t equals 2, we're slightly below 850, maybe 845. So when t equals 2, duck population is 845. And this is representing 1990. It's 2 years after 1988. 1991 we want, 1992, and 1993. We don't use these big numbers because of how they've described the function. They want t to represent years after 1988. And that's done because often they'll do that for functions because you don't want to be putting in like huge numbers and cubing them and squaring them. So they'll sometimes just shift the function so that everything starts at a certain year, and then you're dealing with smaller numbers as your inputs. So this will be t equals 3, this will be t equals 4, and this is 5 years after 1988. Okay, so let's go back and figure these out. T equals 3, 1, 2, 3. Okay, so again, this was 850, so maybe like 830 for 1991, and then 1992 will be 4 years after, 1, 2, 3, 4. So this is right under 800, and remembering that this is right here is probably about 700. So really close. I'm going to say like 795 when we reach year 4. And then year 5 right here. Okay, remembering that this right here is 750. And so this would be, maybe like 10 more than 750 would be an estimate, so 760. Okay, so we estimated from the graph the births in each year. And if they wanted to find an exact number, you could actually put these numbers in for the variable into this function. But you can see that estimating from the graph is way quicker than putting in each of these numbers and having to do all these algebraic operations for each number. But sometimes they might ask you to do that, and that's totally fair if they want a more exact answer. But the graph gives us a good estimate of how things are moving, how things are changing. Okay, here's our next task to do. Solve n of t equals 500 for t. I actually want you to pause the video and see if you can solve this on your own. Okay, so you've had a few minutes to think about what the solution for this. Basically, we're looking for the input when our output is 500. Okay, so output being 500, here's 500 right here. And so we want the input when our output is 500. It looks like it never actually happens. The duck population is always larger than that. So to that, we would say there's no solution because this never happens. So here's another one to think through. Solve n of t equals 800 for t. This one does have a solution, actually has multiple solutions. Pause the video and see if you can solve this equation here for t. So hopefully you've had a minute to think about, for what years does the duck population equal 800? Well, it looks like, here's 800, it looks like it happens right here, and right here. All of these times in here it was bigger than 800, these times it was smaller than 800, and then it gets bigger than 800 again. But there are 3 times when it's actually equal to 800, and so that's what we want to estimate. So right here, let's see, that's probably like, if this is 1, that's probably like when t equals, I don't know, maybe 0.6. So t equals 0.6 it happens, and then it happens again right here, really close to t equals 4. So we'll say a good estimate is t equals 4. And then it happens again right here, and that would be 5, 6, 7, maybe 7.5. So 3 times the duck population gets to be 800, and this would be sometime in the year, let's see, that would still be in the year 1988. This would be in the year 1992, and then 7.5 years later would be 1995, sometime in there. So those would be some good estimates: 1988, 1992 at some point, and then 1995. Okay, last question with the ducks. Evaluate n of 7 using the graph. So is this 7 an input or an output value? And inside the parentheses, those are always our inputs. So this is a year. We're talking about inputs here, and this is this year 7, which would also be 1995. And we want to know what n is when t equals 7. And so let's see, this is about 750 plus maybe 20 more, so about 770. So we could say that n of 7, a good estimate, would be 770. So this is a really good example to think about and make sure that you're understanding everything. It helped us first get familiar with Desmos, which you'll use throughout the semester. You want to be able to graph functions. If you see an equation of a function, that you want to be able to graph it on Desmos, and then interpret a bunch of different things. They may ask you for certain inputs, they may ask you for certain outputs. Here they were asking us for inputs, and here they were asking us for an output, and being able to recognize the difference in the questions that they're asking. So this is a great example.
So we don't want to leave this section without talking about a few terms that come up. And the first one that I want to talk about is practical domain. We know that the domain of a function is the set of all inputs into the function. And when we use the phrase practical domain, it's going to mean the domain values that make sense in the context of the problem, of whatever situation, whatever function we're talking about. Similarly, for practical range, again, the range of a function are the output values of the function. So the practical range is the set of range values that makes sense in the context of the problem or the context of the function. Let's take as an example the function f, which takes as its input values a car's speed and gives as an output value the braking distance of the car. And so we want to think, what's the practical domain of this? What are the practical inputs? And the practical domain would probably be something like 0 to, I don't know, 120 miles per hour. You definitely couldn't get negative numbers for a car speed. I mean, we're not really considering going backwards. So we would start at 0, and you're not going to get much higher than 120. You're not going to get like 5,000 miles per hour for a car. So this is a good practical domain for this type of function. And then a good practical range might be something like 0 to, gosh, I don't know. I really have no idea, but I'm pretty sure you're not going to go bigger than 2,000 feet. You're not going to go like, your braking distance isn't going to be 20 miles. So this would be a good practical range, and we're not going to go negative. You're not going to have negative braking distance. Okay, so I just wanted to touch on what these phrases meant. For our last example, we have the following function. Okay, here it is. This is our function, and this is the only information I know about it. I don't have a formula, I don't have a table, I just have this graph, this picture of input and output values. And we're going to answer a series of questions just based on what we can see here. And the first question is, what is the domain of f? So this graph is representing our function f. Let's see, domain has to do with input values. And it looks like, and input values go along the horizontal axis. It looks like this function starts right here, has a bunch of values, and ends right here. So my starting input value is -4. And we go all the way through to right here where my ending input value is 6. So I'm going from -4 to 6. And this is how I'll write it. This is called interval notation. And you have a starting point and a stopping point. And these square brackets mean you're going to take all the numbers between these two numbers and including these two numbers. So my domain for this function is from -4 to 6, including those endpoints. The next question is, what is the range of our function f? And so range has to do with output values, which is always on the vertical axis. So of this whole function, what are like my lowest output values and what are the highest output values? So lowest output values happen about, it's all contained within here. This is kind of the low point here. So what's my y value there? It's -2. So it looks like I'm going from about -2 to, and what's my high point for an output value? It's about right here, which is 3. So from about -2 to 3 is, and all the numbers in between, that's the range of f. The next question is, what are the x-intercepts? So this is a phrase that is important to know. This means, where does the function intercept the x-axis? Okay, so here's the x-axis right here. And where does my graph, this red line, intercept that axis? It happens 3 times, right here, here, and here. So I say that my x-intercepts are x equals 0, x equals 4, and x equals 6. This is a good question. For what values of x is f of x less than 0? So sometimes we want to know, when is the function positive, when is it negative? And so here we're asking, when is the function f negative or less than 0? So when is this function negative? When does it dip below the x-axis? Well, it looks like here are all the values where it's negative. And so we could say when x is between 0 and 4. So we can write this using interval notation, or you can write it using inequalities too. So we'll do both here. So the function is less than 0 between 0 and 4. I could write it like that, or I can write it like this. Or when x is between 0 and 4 can be written as 0 is less than 0 is less than or equal to x is less than or equal to 4. This is like a problem we've seen before. Solve for x, f of x equals 3. So the part we don't know is the input value, and the part that we do know is the output value. So when is the output value 3? For what input value is our output value 3? Our output values are along the x-axis. So 1, 2, 3. And the point that our output value is 3 is when x equals 5. So that's the solution for that one. One more similar to that, solve for x, f of x equals -27. So when is our y value -27? Here's our y-axis. We would go all the way down to -27. Actually, this function is never -27, so the answer is no solution. There is no x value that would make our y value -27. It just never happens on this function. Okay, last question, actually 2 questions in one. Find f of 2 and f of -2. F of 2, this means that when our input value of 2, they're asking us to find the f, the value of the function. So when our input value, which is along the horizontal axis, when input value is 2, that's about right here, what is our output value? What is the function equal to? When input is 2, our function output is -2. So this equals -2 here. And then the next question is, what is f of -2? So we put on our input axis, we go to -2, and we see what the function is doing. What's the value of the function? And it is 1. So f of -2 equals 1. Great. Okay, that's the end of that. So some of the important things that we have been practicing and learning today were that we were able to read function information from a graph, and we're getting more comfortable with function notation. We also were introduced to the graphing tool Desmos. You definitely want to check that out and get more comfortable with it. All right, good job.